two, 1, 2. It's 9:12 already, so I'm going to start the lectures. All right. Welcome to lecture 10, the 10th lecture. In this lecture, the topic is quite technical. You may not see this topic in the database course, since a lot outside, because not many people teach it in the very fundamental database course like this. But well, once I try to modify, adjust the curriculum for this course, I think that this topic is very important, especially if you want to use database management system well. That is why I include this topic in as one part of these class lectures. Well, to understand it deeply, it's definitely hard because you need to require many background knowledge. But well, for today, I'm not gonna get into that deep. I'm gonna go into the surface of this topic only. Okay? So today's topic is about query accelerations. Query accelerations means to improve the performance, to accelerate the queries. When you're talking about performance is likely means performance likely means the speed of the execution. Right? So let's say when you query something, well, so far in the lab, when you query something, you've got the result so fast. That is because you are working on a very small data set. But let's say that you are working on a very large organizations or an applications that require tons of data, then one query could take minutes, hours, days, weeks. If that is the case, then you really need a way to improve the speed of the queries. Otherwise, they're going to take a really long time. You know, some queries, you need to run it every day, every night. But if it takes more than 24 hours, then you likely cannot run it every day. Right? You cannot run the query daily. That's a problem. So you need to have some way to improve the speed of queries, right? So that you are able to achieve the requirements of running the query every day. The good news is SP4 will be released next week, and SP3 has already been released. Not sure whether you have seen it or not, but there's no checkout for SP3. That's a good thing, but let me tell you this: if you are doing SP3 requires you to draw ER diagrams. Please use the notation that we teach on in the course, right? Don't use the notation like rectangle and then some weird lines. That won't be allowed in the SP3. So I'm recorded. So I hope on your absence you know it. Okay? So basically just use what we call notations, right? Which is the rectangle and the diagonal shaped relationships. Okay? For in SP3, right? Just submit it. Okay? It can be checked very easily whether you kind of like copy each other's or not for that assignment. Right? That's why we don't need to have any checkouts. Okay? Which means the multiplier will automatically be 1. Okay, so they want me like 0.5x, 0.25x for SP3. Oh, by the way, for SP2, for the recheck out, I haven't released that information yet, but perhaps it's going to be within next week. I will give you like maybe 7 days to do recheck out for SP2, right? For SP4, it will be out next week. The topic for SP4 heavily relies on today's lectures. So please be focused. Let's talk about some motivations. Let's see if it's okay. Why this lecture is important? Let's say we create a system, a social network system, where when you enter the profiles, like your friends' profiles, you see all the information, including the profile pictures, the names, the cities, the birth dates, the whatever they want to show you, right? So if you want to do that, let's say you click on the profile pictures of people, right? Let's say user ID of people is 100, right? You're gonna put 100 into this, and then we can try queries. This one will query every single column, right? For the row whose user ID is equal to whatever you want to put in, right? If user ID is a primary key, then there will be definitely one row, at least one row, at most one row, getting to be in the result, right? So I hope so far you understand this query, right? You know what this query does. Okay. So let's say if you do this naively, imagine that you need to write a Python code to do the equivalent process as this query. Then it's likely that you have a CSV file on the table, right? And you write for loop and loop through each row in the CSV files. Then you check whether the ID matched with the ID in the CSV file for each row. And in the worst case, you need to run through all the single rows, right? In order to see whether there is the row that has the same user ID or not. That's definitely taking a lot of time. We call, when they try to read the entire tables, or the entire table, we call that process table scan, right? So basically, if you do this, you need to do one clean table scan in order to get the row. So let's assume that when you read one row, it takes 1 millisecond. 1 millisecond sounds good, right? It's just a blink of your eyes. Just blink, and you get one row already. Sounds still good, right? But a table scan means that you need to read the second row as well, which let's assume that it takes 2 milliseconds. Then you read the next row, it takes 3 milliseconds. Then you read the next row, it takes 4 milliseconds, and so on and so forth. Whenever you reach the end of the table, you now takes n milliseconds. N milliseconds. Let's say your table contains 1 milli rows. It takes 16 minutes now for 1 million rows. You just want to get a user profile, but it takes 16 minutes. Oh, you can imagine you get into Facebook, Instagram, you can click on that profile and you need to wait for 16 minutes. You're not gonna like it. Definitely, you're not gonna like it. So that is why this lecture is important. Query acceleration. When people typically, when they are working on a very large data set, like social network where there are tons of users using it, then they really need some techniques to improve the query speeds. Oh, by the way, just to note that this lecture can be very short. There is not much context, right? So, we know that the problem is that given we need to scan the entire table, definitely take a lot of time. Not worth it, right? It's not worth it. But, well, actually, we only need 1 row, right? Out of n rows in the tables. So, why don't we try to think about a strategy that is kind of like better than this? Okay, so let's have some strategy. So now we have these tables. I only showed you user ID, but let's assume that this row contains other contents as well, contains the values of other columns as well, right? But this is the primary key, right? So given this, I want to find user ID 118. So how to do it? The strategy number 1, why don't we just not scan the entire table when we stop, when we found it, right? That sounds good. That sounds like, that makes a lot of sense, right? We just don't need to scan the entire table. So we start with the first one, take 1 milliseconds, and we move to the next one. Okay, still, I heard some sounds. I'm afraid it's get off. Remove my recordings. Okay, the second row takes 2 milliseconds. But actually, the second row, we got the ID that we want, right? We got the row whose user ID matched with the user ID that we want. So we can stop. We only take 2 milliseconds, right? Sounds pretty good. We don't need to access every single row in the tables anymore, right? But in the worst case, let's say user ID is 1, and the user ID 1 is another table. That's still in the worst case, right? You still need to read n rows, which is not good. Not good at all. So that's why these strategies, on average, you may need to read, like, let's think about it on average. Half of the data are in the second half of the tables, which means half of the data need to take at least Okay, so let's think about it on average. So if you want to get this data, it takes 1 millisecond, right? This one, 2 milliseconds, 3 milliseconds, 4 milliseconds, to n milliseconds, right? Then, on average, it's like divided by n, right? Which is what? Plus 1. Which is n plus 1 divided by 2. Something like that. So it's on average it's like n divided by 2 milliseconds. So still, if you, on average, you need to take like n and a half of n milliseconds. If you get back to the 1 million rows thing, from 16 minutes, now you can get it down to 8 minutes. 2 times better. But still, do you want to access a user profile with 8 minutes? Open up Facebook, click on profiles, wait 8 minutes before you get into the profile. No, definitely not. We're not talking about the pose and the pose as well. That's more cryptic, you know? Right? Still not enough. Like just 8 minutes, still way hard. That is why these strategies, okay, better than before, at least 2 times, but we need more. We need more. Well, if you're lucky enough that perhaps the columns that you want to search. So let's say that this is what we call search key. Right? A column that we want to search. Let's assume that we are very lucky that the values in this column are sorted in orders. Like this, right? 1893, 118, 78, 56, so on and so forth. Right? It gets sorted. We can use an algorithm for binary search. Since this is not an algorithm class, so let's see some animations here to get it better. It's like, so instead of we go through the row of the table one row by one row, we start from the center, right? We start from, let's say we want to search for 47, we start from the center. And we check whether this one is greater or lower than, the key that we want to search is greater or lower than 14. If it's greater, then we can just ignore this part and check only for this part, right? So it's like I'm not sure they have played this kind of things online, but it's just guessing lower or higher numbers. It's like a number guessing game. Yeah. So this is one of the way, but the constraint is that the data in that column, the value in that column, need to be sorted somehow, either ascendingly or descendingly. Okay, so that is the condition that you really need. Okay, so how does these strategies improve the search? What is the impact of these strategies? It seems to be not a very cryptic way, but the power of these strategies is very high. So normally, if you use binary search, you need to read only around log 2n. Have you remembered logarithm? Do you know what is a logarithm? Well, but okay, just for log 2, when you have n, right? Let's say n is 16. When you want to find log 2, you can't just count like. Have you ever count like 1, 2, 4, 8, 16, 32, 4, 64, 128, like that, right? 1, 2, 4, 16, 8, 16. We just cannot use this. Sorry. Well, one of the ways you need to cast this into two something, right? For 16 is 2 to the power 4, right? So log base 2 of 16 is 4. So you just take this as the result of log, right? There is a trick as well. 2 to the power of 10 is very close to 10 to the power of 3, which is 1000. Which is fortunately, luckily, 2 to the power of 20 is also very close to 10 to the power of 6, which is 1 million. And fortunately, 2 to the power of 30 is also approximately equal to 10 to the power of 9, which is 100,000 or 1,000 million. So it's likely that if it is k times 10, it's approximately equal to 10 k times 3. Right? So you divide this by 10, you times 3, you got 10 to the power of this. Right? You divide 30 by 10, you get 3 times 9, you get 10 to the power of 3. This is to approximate it. It's not the exact values, okay? Because if you compute to the power of 10, you're going to get 1, something like this kind of numbers. Okay? So it doesn't approximate numbers, but it's very close. Then you can use this to approximate the performance of the binary search. Let's say you have 1 million values. 1 million values likely to 20, right? 10 to the power of 6, which is likely to be 2 to the 20s. If you find log 2 of 2 to the 20, you get 20. Which means for millions rows, you only need to read on approximately 20 values. From 1 million down to 20 values. Now, the amount of the reductions is very massive. It's massive now. Now you reduce from 10 to 6 to 20. You reduce it by 50,000 times now the performance. So you only need to use 20 milliseconds to get to some user profiles. Well, 20 milliseconds, so fast. When you blink your eyes, perhaps take more than 20 milliseconds. This is good enough, right, for getting to some user profiles, right? For Facebook, let's say they have like 1 million users, in which I think they are a little bit more than that. 1 million, right? 1 million is 10 to the power of 9 users, right? So they only need to take 9 divided by 9 times 3, 27. So they only need to take 270 milliseconds for entering the user profile if they use binary search, in which it suffices, right? 270 milliseconds, less than a second, and you get the user profile. Good enough for even Facebook. I we want to go beyond that, like, let's say we have 1 trillion rows in which there is some tables in the world. Get into that part, but still, even Facebook, I don't think. Maybe Facebook hosts may reach 1 trillion rows, but yeah, you're likely gonna meet it. Let's say you have 10 to the 12, which is 1 trillion. Right? You only need to take like 12 times 3, which is 360 milliseconds. Still less than seconds. Compute correctly. Yeah, see, you only need to take 360 milliseconds for 1 trillion rows. Still very good. Right? But still, if you want to read it, these kind of like massive number of rows. If you remember the last week, right? Last week lectures, we talked about reading from this, right? If you have 1 trillion rows, it's likely that you're not gonna fit the data into a disk. You may need to store the data maybe in another machine, and reading the data from other machines definitely takes time more than this, So it's likely that maybe the most frequent, let's say if some profiles may need to be prioritized, right? Let's say the hot profiles, like some stars, some superstars, some popular organizations, the profiles may need to be cached in a faster memory, a faster data storage, right? And that will link with the previous lecture. Okay? So, but binary search sounds good in terms of logically, right? The number of bits reduced massively. But is it good enough? Well, if you remember, one of the constraints for binary search is that you require the data in the table to be sorted. And well, when you check, when you load some data, some table, the data in the table, they're not guaranteed that they're going to be sorted, right? So, if they're not sorted, we cannot use binary search. Now, sad. So, perhaps we need to take the new strategy that maybe the power is equivalent to binary search. Well, I think we are all agree that binary search is enough to improve performance, but we just need the data to be sorted. How? How to let the data not sorted, but we still get the same power as binary search? This is the last strategy, not the last one, but a good one, which is to add an index. Well, the word index, you may not be familiar about it a lot, or on this word a lot, but if it's talking about table of content, when you open up the book, and you open up the table of content, index is like a table of contents of the table. Before you read all the data, now you can filter it. You just check the topics that you want first by opening up the table of contents on this table. And then, oh, I saw that this is a topic that I want. So I will jump to that page and scan that chapter, right? So that is basically index. Well, technically, index looks like this. Looks cryptic, right? Somewhat cryptic. This is, if you remember what you have, this is something like called tree, right? Trees in graph theory, right? In discrete mathematics, the structure we call a tree. So we basically build up this tree to help aid the search, making the search faster. How fast it is? Almost equivalent to binary search. If you pick it properly. Well, the good news is that for index, we can add it for either a columns, for one column. Let's say this index is for a column user ID. But somehow, when we write a filter, we make one filter like user is equal to 1.8 and image is not now. Somehow we want this kind of conditions, right? We can also build an index for these both of the column as well. Both user ID and image columns. Right? You just need to pack user ID and image column together. So we will add a single value. Okay? So that's all for the motivations. We're gonna jump into each type of indexes, each type of index today. I'm not gonna go into the details, but I'm gonna give you enough information for each one so that you are able to do SP4. Okay? The first one that I would like to talk is a hash table. I have previewed this type of thing before. I think perhaps in lecture that we're talking about data models, right? So hash table is something like this. It's basically a data structure for implementing something that we call a dictionary. So if you remember a dictionary in Python, dictionary is basically you have a table of two columns. The first column is key or vocabularies, right? The second column is basically the values that is associated with a key. Right? And all key here must be unique. Right? So basically it's a lookup table. So when you want to search for the specific user ID, you check the hash table first to see the locations of the user IDs, right? But let's say we have like a million user ID in the user profile, doesn't mean that we need to have a million records on the hash table. If we need to have a million records in the hash table, then that doesn't make sense, right? We still need to read the entire hash table anyway to search for the key that we want. So that's why typically the hash table is a lot smaller than the table itself. Well, but if it is a lot smaller, then how can it carry all of them? How can it like tell whether it definitely cannot fit all the user ID to this one. So how do we find the user ID that we want here? So the thing is that, let's look at a second example. So the key here is not the user ID. It's perhaps, it is instead a hash of the user ID, a hash of the user ID. Right? What is a hash? A hash is basically the result of you putting a value here into the hashing functions. Hashing function is just a mathematical functions. But most of the hashing functions, you need to limit the range, its range, or the result into some specific range. For example, hx here, the result must be perhaps in between 0 to 10, something like this. You need to limit the number of the results. You need to limit the values that you're going to get from the hashing function. How to limit it? How to limit the possible values from the mathematical functions. Let's assume that x is an integer. How to limit it into a certain range. We have learned it before, somehow. Yeah, X is from users.
Then we can check if X is greater than
Okay, that could be one of the possible answers, right? If you write in a mathematical expression, it's like, let's say X is X, if X is less than maybe 10, right? And then let's say it's 0, it's greater than or equal to 10. Something like this, right? Okay, is there any method? So the problem is this, you can see that if X is more greater than 10, so you need to assign to some values, right? So, in distributions of the data, will perhaps, so this is 0, this is 10. On this slide, will perhaps be something like this, right? There's going to be one data, so this is a frequency. This is value. All the data will likely going to be flowing into zeros, right, when you do the hash. Well, let me tell you first why the range needs to be limited. Because we want the hash table to be small, right? So that we don't need to search a lot, right, for it a lot. And instead of we search using, let's say I want user ID 118. Instead of I use 118 to search in the hash table directly, I use hash of 118. If you use the hash of 118, then I'm saying that the hash function here will limit the values to be in the range of 0 to 10. Which means this hash table only needs to contain from 0 to actually 10. But if you do this, then it means that it will be a close range. Something like this. So it will be to 9. Right? So you only need to search for 0 to 9, from 0 to 9. But the problem is that if there are a lot of value zeros here, then if you get to this point, this is what we call pointers. If you point to all the rows that whose hash is equal to zeros, and let's say point to all this row here, then it's still need to search. You still need to look for each row here to match the user ID here with the user ID here, right? The idea is that you use the hash, you search in the hash table to figure some data out. Right? So you scope down the rows that you need to search for. But if we use these mathematical equations or expressions, and somehow for zero there are a lot of values flowing to zeros, then when you get into the first entry, this arrow likely going to point to tons of rows. And you still need to do table scan for that part, which is still not quite performant. Right? Is there any better way to, perhaps what we want the most is, we want it to evenly distributed, right? Uniformly distributed. Have you learned uniform distributions? Have you learned about it? Have you learned about statistical distribution? Do you know the uniform distributions? That is not, that is standard distribution, right? That's normal distribution. Uniform is for all the values. They are likely the same probabilities to get it. Right? That's why we call it uniform, the same. So we want this, we don't want this. How can we form the mathematical expressions that we likely gonna get this?
Use random function?
Well, let's say we use random. Well, yeah, perhaps you will get this, but let's say if you want to access it, you use hash of 118. Well, okay, first there are two problems here. The first problem is how are you going to ensure that the range of the data is from 0 to 10? Or you can, but you can put on the range, right? Okay, that's fine, that's so. The second is, let's say you put 118 into the hash function. For the first time, you may get x, but the next time, you need to rerun it. Okay, you could get something rather than x, like y. You still, the hash function, when you put the values of it, the result should be deterministic. Otherwise, you're not going to search. You could get, okay, the first one you get 0, cool. Then you store the value to zeros, right? The second one, you get 1, you find 1, oh, you cannot find 118 anymore, and you accept that there's the 118. No, you should not do that, right? So random function is still not a good way. Is there any method to limit the values into a certain range? Can you say it again? Len? How? Only talk about, let's say we only talk about the mathematical functions. Right? This mathematical function has one parameter. Now to make sure that all the results of this function must be in a certain range. Let me give you a hint. You may use some operations. It's not likely a mathematical, it's actually a mathematical operation, but you're not familiar with it definitely if you study in your grade schools, high schools. It's not a very popular operations. But I have taught you before in a Python class. Starting with M. Start with M. Right? And follow with O. Think about it. Do you think it's possible to use modulo to do this? Let's consider the function hx equals to x modulo 10. When we model by 10, what can be the possible values, possible results? Can we get 11 from this? Can we get something greater than 10 from this? Can we get something lower than 0 from this? Well, in some programming languages, yes, we could, but if x is like an integer, it's like a positive integer, you likely can guarantee that it will be definitely less than 10. Right? Because you only get the remainders when you divide by 10. Right? The remainders cannot exceed the divisors. Right? So one of the ways to use modulo. And if you use modulo, if you get 0, the result will be 0, right? 1, result is 1, 2, result is 2, 3, result is 3, 4, result is 4, 5, result is 5, 6, result is 7, result is 8, 8, result is 8, 9, result is 9, 10, result is 0, 11, result is 1, 12, result is 2, 3, 4, 5, 6, 7, 8, 9. It's distributed the value results quite uniformly. If the data are like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. Right? So that's why hashing functions typically use modulo, right? To kind of like limit the range of the possible results. So okay, given that we have a hashing function now, then how to use it? Let me recap it again, even though I have said it before, but let me say it formally. So let's say we have this queries. We want to get user 81, right? What we do is we focus on this filtering conditions, user 81, apply the modulo. The modulo is 1, and then you mod it with the length of the hash table, which is 1, 2, 3, 4, right? The hash table with length 4. So it's 1 multiplied by 4. When you get 1, right? You should, so in this point, 1, you get this entry. And this entries, we point to 2 rows. So now, instead of you search for all the rows, you need to only focus on these 2 rows. These middle rows, no need to search for it, because definitely the hash are not the same. Right? You only want to search for only the first or the last row. And searching for 2 rows take 2 milliseconds. See, very good, right? So you check for the first one, okay, doesn't match. No worries. Go to the last one, oh, match, good. Right? So this is something we call a hash table, using hash table as an index. Okay? I'm sorry for this, I haven't done the variation properly anyway. Let's ignore the red part first. The good news for a hash table, the good things for a hash table is that if you have the theory constants that are equalities, like you say equal to some values, this value equal to this, go use hash table. Hash table is one of the very good index that you can use. Right? And another thing is that it would be very good if the values in the filtering columns are also unique. If it's not unique, let's say all of these are ID 1. In which, if it's not a primary key, then it's possible, right? If it's all 1, then if you do hash of 1, you get 1. You need to still need to search for all the rows in a table. Not great. Not quite good, right? So still, the value should be, in the filtering collection, should be unique as well, as much as possible. It doesn't need to be all, and it doesn't need to be strictly unique, but the value should be, should not have contain a lot of duplicates. So, if you got this, cool, good, wonderful, especially if this is primary key. If you do primary key equal to values, perfect. But if you do something like this, age equal to 18, and perhaps in Facebook or in some Instagrams, maybe users with age 18 are millions of them, billions of them. Not quite great, right? So this is hash table. Okay? Any questions, comments, concerns? Not hard, right? This lecture is quite easy, relaxing. Next one, this one we call B-tree. Last offering of this course, I didn't teach B-tree. I teach something called BS3 tree, binary search tree, which is more fundamental than this. But since this course, we're not going to get into a lot of details, and I think that I can just jump to B-tree directly. B-tree is something like this. It's what we call, it's basically a tree. You know what is tree, right? It's basically a tree, but it's what we call an M-way search tree. It's a tree that you could have multiple students. Each node can contain multiple students. And the nodes here, each node can contain more than 1 values. So let's say if you want to search for, so we can construct this tree on top of the column. Right, let's say I construct this tree for a user ID column. Then I'm going to get this. And then we want to search for it. So I'm not going to talk about how we get it. Okay? If you want to know how do we get it, we need to read more. It's quite complicated, so that's why I'm not included in this course. Right? But let's say that there's some magics that you can, in DBP, most database management system that allow you to construct this tree for a certain column for you. So if you have this queries, user ID 1, do the same things. But for this one, you start searching from the root. B-tree say that you check the values here. If the values here that we want to search is lower than the values in the nodes, go to the left-hand side. If the value is greater than the value in the node here, go to the right-hand side. 1 is lower than 58. Go to the left hand side, right? Okay, cool. But how about the node with more than one balance? If it has more than one balance, it means that now we have one more condition. So we have 3 and 6, right? We have 3 cases now. For this one, the first one, if you have one value, you have 2 cases. Lower than 58 or greater than 58, right? If you have 2 values, then we have these 3 spaces, which is lower than 3, in between 3 or 6, or greater than 6. So that's why we have 3 childrens. If it is lower than 3, you move on to the first one. If it is in between 3 and 6, you get into the middle one. If it is greater than 6, you get into the last one. In this case, it's lower than 3, so you move on to this one. And you do the sequential search here. You scan in this node and you get it. So the number of the nodes that the number of the value that we need to read is 58, 3, and then 1. Let's say you want to take 22, then you may need to read 6 as well. Right? But you can ignore these and these. Right? You can ignore a lot of values. So this is B trees. Many DBMS database managers allow you to construct this tree to aid your search for a column or multiple columns. Another good thing for B-tree, actually not the original B-tree, but we have a variant we call B plus tree, which is also supported by many DBMS. For B plus tree, it is allowing you to do something called a range scan. I will tell you what is it, but let's consider this. Now it is not an equality condition. The condition is likely a range between 1 and 40, excluding 1 and 40, right? Let's consider this. Now, for B-tree, if you want to get the range, one of the ways is you get the location of the first values of the bound. The bound is 1 to 40, right? You get the location of 1 to 40 first. So 1 is here. 40 is likely here. Right? Because it's lesser than 58, so it must be in this subtree for sure. Right? Okay, you get this kind of locations. Then what we're gonna do is you can scan the leaf nodes, this part. You look at all the values in the back. For the original B trees, these nodes are disconnected. The data are stored separately. But for B plus tree that I told you, the data in this node are connected sequentially. So they are close to each other. So when you do this scan, you easily gonna get a very easy localities in which the scan here will be very fast because it's likely gonna group together data here. Right? So this is using B tree, actually B plus tree to be precise. With B plus tree, optimized for range queries, in which many databases use B plus tree, either B tree or B plus tree. Well, preferred workloads for point query is still good, not bad. But hash table maybe could be a little bit good. If the hashes are uniformly distributed. If not, then you can get into some chaos, right? But for range queries, if you use B plus tree, then definitely it's better than hash functions. I'm sorry, have the hash table. Why? If you imagine the hash table, let's say I want the data from 1 to 40, and you use the same old hash table. 1 to 40 is likely you need to read all the things, right? It doesn't help. Doesn't help figuring out some values, right? You need to read the entire table. It doesn't help that much. Okay. The next one, not the same. Now we are not focusing on. So far we're talking about numerical values, right? Numbers. Hash table. If you encounter floating points or real numbers with decimals, for hash tables will be cryptic, very cryptic, you know, because hashing functions. If we have a lot of decimal, then need to have tons of entries, right? Not gonna work well. But for B3, still floating point, good, right? Because we only care about whether it is greater or lesser, right? So another one is, let's say that. Even with real numbers or floating points, right? Also a good thing as well. Especially if it is a point where, so then it means that in my final exam, let's put floating points as floating conditions. I ask you what you should use between hash table and B-trees. Interesting. I should not recall that. Okay, the next one, try. Try here is not try, that means trying, attempting to do something. Try here comes from the word retrieval. Retrieval. And if you look into this word carefully, let's spin the track on this, the word retrieval. Try here is not about numerical values. It's about a sequence of characters, or basically a string. So try here is basically a search tree. Right? A search tree. Okay? So now we have a tree. So try here is a tree on the right hand side. Right, the tree is on the right hand side here. So we construct this tree, right? For each tree here, we are allowed to put in strings. I think let me open up the visualizations. It will help you see how it gets constructed. So let's assume that we have this table. So I love to use this website, very useful one. Okay, for try, when we construct try, we kind of like insert a string one by one. So let's say we insert guy named Tim, right? Put it here, then we construct a tree like this, right? A try is also a tree. Okay. So what good about this? What good about this is when we look for a condition like this, you start from the first one, you want to find a prefix on it. You check the A here, and you get all the subtrees on this one. you scope them using the character, the prefix of the strings. So to make it more clear, let's add more people with a, like, what else do we have? Okay, let's add this guy in. Implicit, right? Add in here. So you see how it gets constructed? Which means, if we get A, then all these two is the scope of our search. And for the prefix. Then add another A. Andrew. See the good things? If you want to find the guys whose name starting with A and N, then you check for A, you check for N, and then all of these are the guys who the prefix of the names are A and N, A-N, right? So this is try. It's allow you to reduce search by using the prefix of the strings. Is it clear to you? Right? The way to construct it, I don't think it's hard. As you see here, it's not quite complicated to construct it, right? Not like V3 keywords. Okay. So let's say you want to search for this guy whose prefix starts with NA, right? What I do is I start from the top, right? And then check for N, and then check for A, and that sub-tree will be your results. So, but you see, actually to try, you need to go follow it one by one until you get all this pattern. Okay, so now you got this record. Okay. So the leaf node of the tree will point to the row. Okay, so I can say it's quite fit into string queries. But it doesn't mean that it doesn't work for numerical values. Let's say I have you can think about numbers as a sequence of characters as well, right? So we could construct a tree like right? This is a number tree which is use tries. Somehow it could be better as well to do this, depends on the workload. Right? But well, most likely the problem with this is that you definitely, when you have them, you're definitely gonna have a lot of nodes here. Right? Because you need to store every single digits. But if you use B3, you don't need to store like every single digit, right? Because you need to store the range for each one, whether it's greater or lower, later, right? So this is tries. But this also works as well. It also helps you accelerate the query as well. So try. Okay, lastly, zone maps. Zone maps is actually the thing that I have talked before in lecture 3. So this is lecture 3 without organizations. I promise to you that I'm going to teach you this in lecture 10, if you remember that. And this is lecture 10 now. We fast forward to the lecture 10. So, zone maps, another term for zone map is what we call min max index. It's basically when you have a table, right, you chunk the table into multiple chunks. Let's say chunk 1, chunk 2. And for each chunk, you kind of like compute some statistics of each column. The mean, mostly it's going to be the mean and the max. And let's say the mean of this, let's say we talk about the mean max index of the user ID. And the mean here is 1, max is 10. Mean here is 5, max is 100. If I want to search for user ID 1, do we need to get into this chunk? No. So we can skip entire chunks here. That is the min-max index, or what we call zone map. There's also another benefit of zone map as well. Depends on the statistic here. Let's say if you want to find the maximum values of the entire table, you don't need to actually look into the values in each chunk. You only need to read the max of each chunk. If you want to find the sum, and if you also store the sum for each chunk, you can just add all the sums up without the need to read the actual data. So there is zone map. Zone map used a lot in the database that we call OLAP DBS. OLAP, are you familiar with this term? Analytical processing, which is the workload that tends to summarize or analyze the data, doing data analysis on the table. And most of the time doing data analysis, you want to find a summaries of the data. Finding a summary of the data, most of the time require you to read the entire table. So reading an entire table, even though you have hash table with that, you have B-tree, that you have try, but if you still need to read the entire table, that doesn't help. The one who help is zone map. Then you summarize the chunk first, and if you want to find the sum, you only pick the pre-computed sum for each chunk and add them together. You now reduce the number of read. Right, the number of addition as well, we want to find sum. Right? Okay, so this is one called zone map. Last year, in my midterm exam, last year we had a midterm exam. I asked students what is zone map as well, but I haven't taught them. But it is in the prerequisite that I should put in something that you should study by yourself. But it is a bonus question. It's also about it's kind of like since I think that I haven't taught them, so I put it as a bonus questions. So the scores doesn't count into the what should you call it? It's bonus. It's just bonus points. Yeah. The purpose of it is to skip reads. So someone may call it a skip index as well. But the skip index, it doesn't need to be only zone map. Zone map is one of the way to create a skip index. If you put some in it as well, you may not want to call it min-max index. Because min-max index sounds to be like only min and max, right? But if you put some pre-computed statistic, then likely not going to be a min-max index. Likely going to be what we call zone maps. Okay. Lastly, is index selections. I'm not going to teach you how to choose between hash, tree, trie, zone map. It depends on you, given what I have taught you so far. But my question is, okay, given we know that we can accelerate first, but which column should we put on those indexes? I tell you that we can put an index onto a column, or group of columns, but how to determine which column should we put on index? Right? Because building an index also costs you something. If you insert new values, if that table, you keep inserting new values like a post, right? In social network, people keep posting something every single day. And if you per somehow create an index on that table, on a column of that table, those index will need to be modified every single time you insert new values. So the time for adding new rows will be amplified. Instead of you need to write down new rows into a table, now you also need to add new information to the index as well. So this is trade-off, the major trade-off. Right? Given this major trade-off, you should not put on index on every column, even though it's text. Also, adding an index will increase the storage that you need to use. It could be double of your storage. Not great. Not good, right? So, how do we decide? One of the non-scientific rules that people love to use is using selectivities of the columns. Not the column. Selectivities of the queries. Selectivity is the proportion of the row expected to match the conditions. Let's say user ID equal to 1. The selectivity of it is likely to be 1, right? Because that is the row expected to match the conditions, right? Over the entire tables on O(n), which is likely, if the table is very large, it's likely to be 0.000000001%. If that's the case, should put index on. But if, let's say, your conditions kind of match with half of a table, perhaps just do table scan, come on. Just do table scan, then just read out some unmatched, right? You don't need to spend extra space on it, and also trade it off by when inserting into that tables, you double the cost of the insertions. You don't need to do that, right? You don't need to, you don't need to increase the cost of insertions. If you know that you need to read like the entire table anyway, right? So the non-scientific rule say that if the selectivity is less than 10%, then just put on the index on. See more on the left. Okay, left next week, right? Or indeed, no, he's sleeping now. That's it. Indexes are wrong camera. I'm sorry. Indexes are easy but good performance accelerators. Easy one. When you create an index, you will see the line. You only need to say create index on this table, on this column. That's it. You get a very good performance already. Right? But yeah, again, indexes increase your storage memory usage. So think carefully on how to, not how to use them. Oh, sorry. On whether you pick them, on whether you want to apply them or not. Right? On applying them. Right? Next up, P&D will teach you how to improve performance using indexes. That's it. Oh, that's just so good, right? It's good. But next week, I think the next week content is quite dense. Given when I taught it last year, it took me 2+ something hours. But I will try to make it easier, okay, if possible.